So good afternoon, everybody. My name is Derek Zhao. I am a master's student in data science at Columbia University up in New York, and Loc Tran is my mentor. This summer, we've been working on using variational autoencoders to extract explainability from neural networks. And that probably sounds like a bunch of random sci-fi words right now. So we'll start with some technical background and do a brief project overview. Then I'll get into what I did this summer, and then we'll wrap up with some concluding thoughts. So the project that I work on is called Attractor, and it has two main goals. The first is to improve the reliability and trustworthiness of autonomous systems. And the second is to increase people's trust in these systems. And we can accomplish both through explainable artificial intelligence. And there are two reasons why we would want to do this. The first is that people tend to trust the decisions that an algorithm makes more when those decisions are backed up with justification from the algorithm. And the second is that autonomous systems are increasingly more reliant on deep learning and neural networks to make these decisions for them. And neural networks are among the blackest of black boxes. So what is a neural network? Suppose we had a binary classification problem where we wanted to decide if an image was of a person or of a cat. Well, an image is defined by its pixel intensity values, so we can unroll the image into a long, skinny vector, pass it through to the neural network, and the network will give us a decision about what it thinks the image is of. Under the hood, a neural network is really just a series of matrix computations. So we take our input vector, multiply it by a matrix, get a smaller vector out, multiply it by a different matrix, get an even smaller vector out, and so on and so forth until we get the network's decision. The values inside these matrices are called the weights of the neural network. And when we say we're training a neural network, what we're really trying to do is find the correct values of these weights so that the network behaves the way we want it to. Each matrix multiplication is called a layer, and the outputs of each layer is an activation. And neural networks are such black boxes because there are no human interpretable meanings to these weights. And as a result, the activations are also not human interpretable. So my small piece of Attractor is to try to extract some explainability and interpretability out of the internal computations in a neural network. So one way to think about what a neural network does is that it's progressively compressing the input data into increasingly more compact representations. So one thing we can do is instead of compressing the input data all the way, we can just compress it halfway and then try to decompress the data such that we get the original image that we fed in. This type of architecture is called an autoencoder, and it's comprised of two parts. The encoder network, which takes the input data, compresses it to a latent representation, and a decoder network, which takes the latent representation and then tries to generate a reconstruction. And we train this type of architecture by minimizing the reconstruction loss. So why do we care about autoencoders? Well, because an autoencoder's output is an image, this gives us an interesting way to try to peek inside the neural network. So what we do is we take an image, pass it through to the encoder, get a latent representation out, and then we perform what's called a latent traversal, where we take a single component of the latent encoding and we slide it around to see how it affects the reconstruction. As a first step towards trying to understand what these activations do, it's not too bad, but there is a critical problem, which is if I were to ask you to describe this transformation, it would be very hard to do succinctly because too many aspects of the image are changing at once. So we call this latent traversal an entangled transformation. And if we pop over to a different component, it's a different latent traversal, but the problems remain the same. So there is a type of autoencoder called the Variational Autoencoder. We can call it VAE for short. And it's different from a vanilla autoencoder in that the encoder network doesn't directly output a latent encoding. it outputs a latent distribution from which we sample a latent encoding, and then the rest of it is the same. This architecture is trained through minimizing the reconstruction loss and an additional term called the latent loss. And the reconstruction loss and latent loss are diametrically opposed, so if we try to minimize one, we end up increasing the other. So the model gives us a hyperparameter that we get to choose, for which we get to choose a value called beta. And this hyperparameter essentially tells us, allows us to choose what the balance is between the latent loss and the reconstruction loss. And it turns out that if we set beta to a high value, we get much cleaner latent traversals. And so on the left, you see latent traversals from a model where beta equals 0. So functionally, this model would be the same as a regular autoencoder. And on the right, we have a model trained on a high beta. And we can put a word to this now, or words. You could call this the face rotation, or a change in the face's azimuth. But there is a trade-off that we have to make, which is when we set beta to a higher value, we do get cleaner latent traversals, but the reconstruction quality is lowered. And so here you see that there's the original images in the top row, and the reconstructions, especially for Anthony Mackie here, are not as good when beta is set to a high value. In this case, even the gender isn't really being reconstructed properly. So that's the background. What in the world did I do this summer? I like to think of this internship as having been divided into 3 mini projects. The first is just getting these models implemented, trained, and tested. So I used TensorFlow to build a beta VAE, as well as a more recent variant called the TC VAE, which I'll get to in a minute. And then I built an experimental framework around these models. I wrote scripts to automatically save and load models, do hyperparameter logging, data preprocessing and management. Most importantly, wrote scripts to animate these latent traversals, since that's really our only means of examining the quality of disentanglement in the latent space. And then finally, we tuned and tested and trained these models on the Celeb A dataset, which is really just a dataset of 200,000 celebrity faces. A quick note about the TC VAE. The regular VAE loss function is the reconstruction loss plus beta times the latent loss. And the researchers behind the TC VAE discovered that the latent loss actually decomposes into 3 different terms: the image detail term, the total correlation term, and the discontinuity term. And they argue that by placing a beta penalty weight in front of the latent loss, we end up penalizing the image detail term. And that's partly why when we set beta to a high value in a regular VAE, that we lose reconstruction quality. And so their solution is to just put beta in front of the total correlation term and leave all the other terms alone. This seems simple enough, but getting this thing implemented was easily the most difficult week that I've had in this internship. But it was all worth it because the latent traversals that we were able to get out of the TCVAE were fairly breathtaking. So here are some pose-related latent traversals. We have azimuth on the left and elevation on the right. There's color-related traversals. So we have on one side image saturation and color temperature. The VAE is even able to model emotion. So in both latent traversals, you'll see a smile. And on the left side, there's a mustache that's forming. There are also hair-related traversals. So you have the hairline and the direction of the hair part. And there's one that's so cool, it gets its own slide, which is the coolness-related traversal. So having implemented these models and tested them and trained them, Locke and I wanted to develop a user interface for more flexibly exploring the latent space and to also be able to test a larger variety of inputs to the VAE. So we developed an app called Moisturize after a famous Doctor Who villain. And the app is pretty simple. You set a input, so you can decide whether you want to take as input a static image or a webcam stream. You do some light preprocessing on it. Really, it's just changing the zoom factor or doing XY translation. And what's cool is that as the input changes, we get real-time updates on the latent distributions that's being output by the encoder network And at the same time, we also get live updates on the these are the latent distributions output by the encoder network, and then we get reconstructions that are output by the decoder network. And in case we were curious what the reconstructions would look like had we altered the latent distribution slightly, we can do that as well. So I've got a video here. So you'll see as the input changes, we get live updates here on the latent distributions. I'm going to try to get the model to recreate face rotation. And then I'm going to smile twice. You can look at the reconstructions, and it should be able to also model the smile. And also then you can play around with the model. Again, if we didn't have this, we wouldn't really be aware of these specific behaviors. And then you can freeze the image. And then that will expose sliders, which you can use to explore the latent space yourself. I think it's really important to note that this app is not face specific. So had we trained our VAE on a different data set, like say the footage on the dash cam of a car, this interface would still be relevant, since all we would need to change are the labels on all these latent sliders. But the principles are the same. You change you look at your input and you see how it's being reconstructed. So aside from being an interesting novelty or a party trick, Moisturize does have some practical applications. First, it allows us to really quickly test what the boundaries of the VAE is, what it reconstructs and doesn't reconstruct well. It also allows us to very flexibly explore the latent space, evaluate the disentanglement quality, and also look at the interactions between different latent variables. And this all adds up to developing an intuition, essentially, about how neural networks see the world. So these first two mini projects were what Locke and I had planned for the internship. We were able to finish them ahead of schedule, fortunately. So we set our sights on a stretch goal, which is to use VAEs for anomaly detection. And the motivation behind this is that when machine learning systems fail, it's very rarely the case that there was a bug in the algorithm or the math somehow didn't work out. It's almost always the case that the data that we passed to the model to train on just wasn't good enough. It could have been biased, there could have been unwanted correlations, or the data might have been too narrow for the application that we wanted to use it for. So it's very important to us to have a model that can assess whether the input to a machine learning system is outside that system's range of experience. So the way that we can go about doing anomaly detection is, given an image and a trained TCVAE, we can extract some features out of the image. There are the latent encodings, and there's also the reconstruction, from which we can calculate a variety of reconstruction losses. Then we train a binary classifier on these features, and that binary classifier can tell us whether or not an image is anomalous. So to test this procedure, we trained a TCVAE on 200,000 celebrity faces. We held out 1,000 images for testing, so the model wasn't trained on these 1,000 images. And then we picked 100 random non-face images to mix in with these 1,000 test face images. It turns out that training the binary classifier at only the latent encodings didn't work terribly well for us. It did better than random, but it still wasn't particularly good. But the reconstruction losses, on the other hand, were a different story. So each plot here is a different reconstruction loss, and you can see that normal images typically have a much lower reconstruction loss than anomalous images. So this was an encouraging sign for us that we would be able to do anomaly detection on these features. And when we trained a variety of binary classifiers on these features, we discovered that the simple, humble logistic regression actually performed best for us. We were able to get an average precision of 0.86. The average precision is like accuracy, but sort of a more refined metric. It's between 0 and 1. And it amounts to being the area under the precision recall curve, where precision is the proportion of predicted anomalies that actually are anomalies, and recall is the proportion of actual anomalies that got predicted as anomalies. It's a little bit of a brain teaser. So by way of example, if we required that our model be able to predict correctly 80% of what we know are anomalies, then the price we pay for being so aggressive is that 30% of what we predict will be false positives, or images that weren't anomalous that we thought were anomalous. 0.86 for average precision is actually pretty good in most applications, but we can do better. Here are two images that were anomalous images that got predicted as not anomalous. And the reason was that simply the reconstruction loss between the original and the output was just too low. And this is incredibly unsatisfying because this is clearly an image of an elephant, and this is your worst nightmare. So what we did instead, or what we did about this, was that we wanted to use a pre-trained neural network as a feature extractor. I chose the VGG16, which is just a pre-trained convolutional network. It's capable of classifying 1,000 different types of objects, but we're not interested in the object classifications. We're interested in the internal activations of the neural network. And so the process goes like this. We get an image, we pass it through the TCVAE, we get a reconstruction out. Then we pass both images through to the VGG16 to get the internal activations, and then we can compare these internal activations and add these features to our reconstruction losses and train our models. And what happens when we do this is that we get a marked improvement in the ability of a classifier to discriminate between anomalous and non-anomalous images. So our average precision here went from 0.86 to 0.94. These are the kind of results that data scientists salivate over. So when I first saw it, it actually seemed too good to be true. So I ran 100 different experiments on different training and test splits. And this curve is actually the average over all 100 of those splits. The last thing that we wanted to look at was, well, we know that there is a balance between the reconstruction quality of the VAE and the level of disentanglement that it has. So we want, and that those two things are controlled through the beta hyperparameter. So we wanted to also see what beta does in terms of affecting the quality of the VAE as a feature extractor for anomaly detection. So we tested a bunch of different models, trained on different beta values, and it turns out that beta at around 16 gives us better anomaly detection than beta at 1. Our hypothesis going in was that if our model can reconstruct images better, then it will also be able to do anomaly detection better. And to get better reconstructions, you set beta lower. But this turned out to not be very true. And if the previous result was too good to be true, this one was too weird to be true. So you just do the procedure over and over again, 200 times. And this ended up being the average over those 200 iterations. So we're almost there. As far as what we can do next, there are a couple of things. The first is that we just need to test the TCVAE on different data sets. I'm not saying that the results will be good just because it's here on the easy end of the spectrum. I'm just saying this is easy to test and do. Because it has been shown that VAEs do struggle on data sets that have more variability and noise in them. So we need to see what the boundaries of the newer and improved TCVAE are on more challenging data sets. I mentioned a bit how we used an internal activation of a pre-trained network to try to help out with anomaly detection. I would be very curious to see whether the depth of the internal activation will help and how that affects anomaly detection. Also, I mentioned that training a binary classifier on just the latent encodings didn't do particularly well for us, but we were able to get better than random results from it. So a quick thing to do is to merge the latent encodings and the reconstruction loss and pass all of that to a binary classifier and see if the whole totality of data can produce better anomaly detection. This one is a little hard. The variational autoencoder is an example of an unsupervised training algorithm. What that means is that it's agnostic to whatever classification task that we have at hand. So if we given a data set given the same data set, if we wanted to do gender classification or emotion classification, the kinds of latent traversals we get out of a VAE are the same. And based on the traversals that you had saw previously, you might intuit that it'd be much harder to do classification of emotion than to do classification of gender. So this is, there's some research in doing supervised training of variational autoencoders so that if you, say, had a gender classification problem, then you can get more latent traversals that are relevant to gender classification. And finally, this was a question that the net had a couple of sprints ago about being able to measure the quality of disentanglement in the latent space. And there are some metrics that we can use as substitutes. There are some metrics that work well, but only in very specific situations. None of them are particularly practical. So this is, I think, a very hard problem because, well, no one's thought of it yet, and this would actually help VAE research a lot. And then finally, VAEs have a lot of different and very cool applications. There are 3 that I think are relevant to us at Attractor. The first is just model debugging. Let me go back. There are 2 spectrum that kind of coincide. The first is the level of expertise you need as the level of machine learning expertise that you need to benefit from the application. And the second is sort of how ready are we to use this application now? And so on one side is model debugging. You're a machine learning engineer. Your neural network classifier has a 10% misclassification error rate. What do you do to figure out what's going wrong? Well, right now, you just look at those 10% of images that are being misclassified. If there's a lot of them, then you just sample out those images and physically look and try to see what's going wrong. This is an incredibly haphazard and tedious and time-consuming way to try to debug a model. And so with a VAE, what you can do is you can take all the misclassified images, get some latent encodings out of them, aggregate those latent encodings, take all your correctly classified images, do latent encodings on them, aggregate those, and compare. So this is a pretty, I think, this is low-hanging fruit that we can use now, get now, from the VAE. Anomaly detection we already talked about. And finally, there's explainable AI. My opinions on this are basically that because the VAEs are not trained through supervised learning, it's a bit of a crapshoot whether or not they can be very useful for explainable artificial intelligence, depending on the application that we have at hand. So I think if we can get more progress on research towards supervised training of VAEs, VAEs could be exponentially more useful for XAI. I learned a couple of things from this internship. The first is I got over my fear of TensorFlow and Kyvie. I've also seen Locke, the master, at work for Vim and Terminal. I am still a grasshopper, but now I have aspirations in life. I've had some really interesting conversations with Jim E. about reinforcement learning. I came in here not really that interested in AI, but through our conversations, Jim has severely changed my mind, and he's been really helpful in getting me materials towards learning about this brave new world. Brian was super helpful in filling in some very critical gaps in my aerospace knowledge. Chase has introduced me to just the most amazing and intelligent, epic space opera that is Babylon 5. And I know Erica has heard us jabbering on endlessly about it in the mornings. I'm really sorry about that. But I think that each of you should watch this show so that you can join Chase and me in the endless jabbering. Speaking of endless jabbering, there's another show that I think all of you need to watch. What's it called? Come on, someone! Yay! Zen lesson number 45. There is life before the expanse, and there is life after the expanse. Andrew taught me that South Dakota does too have things. Skylar makes really awesome paper airplanes. So it's one of those things you know in theory, but it's still breathtaking when you actually see it in real life. Peyton taught me that's pronounced pescatarian. Yeah, let's move on from that quickly. And I didn't drink coffee before, and now I do, thanks to Tu's persistence and insistence. And I'm actually kind of hyped up on coffee right now. And finally, there's the most important lesson that any intern could learn, and that is you all are the absolute best. And this internship, this experience has been just so much better than anything I could have hoped for. So I'm going to miss this place. I'm going to miss the old place. I'm going to miss all of y'all very terribly. So thank you for the lessons learned and for the good times. And that's it.
Thank you.
What was your favorite part? I don't know. There's a lot of parts to it.
Oh man, my favorite part. I don't know, the beginning was pretty cool. Like just because I didn't really I came in as more of a, data science at Columbia is much more about data analytics. So just coming in and running these models and seeing,
NASA audio conference.
yeah, and seeing the faces more like that just told me that yes, like I made the right decision to come here. Yeah.